Okay, do you think it's time to start, Ryan?
Yeah, I think that's good.
All right. All right, everyone. Thank you for being here today, taking the time to watch this webinar. My name is Alejandra Peralta. I'm an application engineer lead and solutions engineer consultant for the CHEMCAD product in DataCore. I'm a chemical engineer, and I've been working my entire career in process simulation. Today's topic is the simulation for circular economy, best practices learned from modeling plastic resin recycling. Just a quick note before we get started. This is a famous quote from the General Director of the WWF, the Worldwide Fund of Nature International, Marco Lambertini. He said, not only are plastics polluting our oceans and waterways and killing marine life, it's in all of us and we can't escape consuming plastics. Plastic has become an essential part of our daily lives, chosen over other materials due to their low cost, lightweight, and durability. For many years, the industry has been actively seeking ways to improve resin quality in order to reduce reliance on fossil fuel derivated plastics and move closer to truly closing the loop in plastic life cycles. Process simulation software plays a key role in enhancing the efficiency, scalability, and sustainability of plastics recycling technology. It enables engineers to test different operating conditions, optimize energy use, improve quality, and scale up processes more effectively, all without the cost of the risk of real world trial and error. This leads to a more efficient, environmentally friendly, and economical viable recycling solutions. Today's agenda. In today's agenda, first, I will start with a brief introduction to circular economy and where plastic resin recycling fits within the broader context. Next, we will explore why process simulation is such a powerful tool in this area, especially when it comes to designing and optimizing recycling systems. Then I will share some best practices and lessons learned from our experience modeling plastic resin recycling processes. We will also look at how simulation supports sustainability goals and help the industry adapt to evolving challenges in this sector. After that, we will dive into a case study that we model in CHEMCAD. And I will walk you through the process design, the components we use, and the approach we took. Finally, I will open the floor for questions and discussions and wrap up with a few key takeaways. What is circular economy? The circular economy is all about keeping plastic in use as long as possible. Instead of tossing the bottle that we have in our hand or any of the products that we have in our desks or anything you have in your kitchen that is made of plastics. The idea is to design systems where plastics can be recycled over and over again without losing quality. But that's easier said than done. Right now, a huge amount of plastics end up in landfills, oceans, and environment. One big reason, a lot of plastics products packages are made for one-time use, and they're not designed to be reused or recycled. Another challenge is cost. Virgin plastic, or the plastic that is made from scratch, is often cheaper than recycled plastic because the oil prices and tax breaks make new plastic more financially attractive. And then there is a problem of plastic breaking down over time. Each time we recycle, the plastic can lose a little bit of its quality, like becoming less strong or less clear or less flexible. Eventually, it just doesn't work as the way that it works originally, which limits the how many times it can be reused. What is the role of recycling in closing the loop? The main goal is to identify the best mix of recycling technologies that can reduce environmental impact, while also maximizing profitability. How can CHEMCAD support you in this area? If we talk about simulation goals and why to use a process simulation software is great to use in this space. First, we think about accurate processes design. Simulation process helps you to design, improve recycling processes. You can test variables like temperature, pressure, energy, all in a virtual environment. This enables you to find the most effective and effective and efficient setup without costly real-world experiments. Number two, flexibility to explore different recycling methods. With a simulation software, you can use and compare different recycling methods, such as mechanical methods, chemical methods, or pyrolysis, and see how changes in feedstock quality or process conditions might affect the outcome or product. This helps you to make informed choices about which approach works better for your goals. Number three, cost and profitability modeling. Simulation tools can help you estimate operating costs and yields, making it easier to assess the economic feasibility of a recycling plant before you get an investment. These support a smarter, data-driven decision-making. So what are some of the best practices when modeling plastic resin recycling? A common challenge when modeling plastics in simulation software is that you may find that most simulators are built for traditional chemicals and hydrocarbons. So resins like PET or HDPE and PP often are in their default databases. One of the things that you can do when you don't have data for the components is look for thermophysical properties in research papers on plastic recycling, or look for polymer databases or data bank, such as Polymer Handbook, MatWeb, or NIST Chemistry Webbook. These polymer data banks are available online usually, so you can research for data for your specific resin. You can also check if you can get data from labs, or perhaps if you have a pilot plant. So what do you do with this data? You can create custom components. CHEMCAD has different correlation to estimate some properties based on chemical structure. The JOVAC and UNIFAC methods are both group contribution methods used for estimating thermophysical properties of chemical compounds. So when you create your component, you can perhaps mix the predictions from these correlations and also get data from those research papers and data banks. Another important decision to make is the appropriate selection of thermodynamic model, depending on the recycling method and the process that you will be simulating. For example, Penn Robinson or SIK might be suggested for processes such as the pyrolysis or gasification. NRTL or UNIQUAC might be useful if you have experimental data available. And UNIFAC when you don't have any data available, so you can have a predictive model to help with the calculations. Another best practice is to have a good understanding of your process. You need to identify the unit operations and break down the process individually, so you can understand each role, each step in your process. For example, if you have mixing or heating or separation, you might identify the proper unit operations to use in your simulation. Understand their functions, clearly define the purpose of each unit op, so you can choose the appropriate unit op in the simulation. You can also use simplified operation or unit operations in the flow sheet. At early design stages, you may choose a simple unit op that will satisfy your requirements and try to avoid any complexity of the model, especially at the beginning. So how do you apply these strategies in CHEMCAD? The case we're gonna look at in our demonstration is an anti-solving chemical process where PET flakes will go through different processes. Okay, but before I go into more detail, I want to mention that this case study that I'm presenting today is the result of a collaboration effort involving the Michigan Technology University, especially Dr. Urkesh Shadari, Dr. David Schoner, Yale University, and Idaho National Laboratory. The full research paper is available in our website and includes an evaluation of additional recycling technologies as part of the broader circular economy study. For this case study, we selected a simple unit operation or simple unit operations that provided a good balance between the model accuracy and computational simplicity. So in the process, as I said, there are like different steps. Some of the steps will be swelling, dissolution, filtration, precipitation, another filtration of the PET, the drying, and then the recovery of the solvents. For this process, we use different unit operations. We recommend some unit operations, and we use some unit operations in CHEMCAD. So, for example, for the anti-solvent addition in CHEMCAD, we use a mixer with the solvent and the anti-solvent. For the PET swelling and dissolution, we use flash unit operations. For the precipitation step, you can either use a component separator of flash unit op. You will see that in the flow sheet, we decided to use the flash unit op, and I'm going to explain why later. For the filtration, you can either use a filter if you have geometry of your filter or a component separator. For the drying, you can use a flash unit up and specify the temperature. And for the solvent recovery, you can either use a distillation column or a flash unit operation, depending on the stage. In here, you can see the link for the research paper I was talking about. And I'm gonna have it at the end of, I'm gonna have the link shown at the end of the presentation again. So let's see how my process looks in CHEMCAD. Okay, so this is the process that we created in CHEMCAD. As engineers, one of the most important aspects when we start building a simulation before we put any unit operations in place or and after we specify the components is to select the appropriate thermodynamic model. In this case, we use UNIFAC because we did not have experimental data. The components we use for this in this flow sheet where we use water as the anti-solvent. We use water as the anti-solvent. We use gamma valerolactin as the solvent, and we create a user component for the plastic, the PET, that we call PET unifier. Let's talk about a little bit about the components that we use in the simulation. So as I previously said, we use G-valerolactose as the solvent for this simulation. This component is in the CHEMCAD database. It's derivated from lignocellulosic biomass, and it is a green solvent. It's also soluble in water. GBL, some people call it GBL, is a cycling ether, a non-aromatic lactone ring with a 5-member ring containing 4 carbon atoms, and 1 oxygen atom. 2 oxygen atoms, sorry. Why gamma valerolactone? We found some research papers that discover that GBL selectively remove PU or the ink that some of the that the PET has without dissolving the PET. We also found that the solvent target recovery and precipitation process had a lower environmental impact than other virgin polymer fills. The other component that included in the simulation, and one of the most important components, is the resin, the PET. The PET consists of a repeated change of hydrocarbons. The component was created in CHEMCAD using UNIFAC leader-cent correlation to predict some of the properties. The component is made from 2 main monomers, ethylene glycol and terephthalic acid. It is strong and lightweight, and it's transparent. In CHEMCAD, the correlation might predict some of the properties of the component. Some of those properties were like the critical properties, the boiling point. And let me go through and see information about my PET. As I said, we use UNIFAC to predict some of the properties. So CHEMCAD with the correlation predicted some of the critical properties. the boiling point, the eccentric factor, the specific gravity. And we found other data in some research papers. When you create a component using the unified correlation, CHEMCAD will add the component contribution and use the structure of the molecule to try to predict the conditions of the component in your flow sheet. I'm gonna execute. Sorry. Okay. So back to our flow sheet. So let's start now. Let's explain a little bit about how the simulation was built. So we started the process specifying the feed stream, the fresh GBL, which is a solvent. And we specify the streams at 25 degrees in watt atmosphere. Let me change and about 1.3 cubic meters per day. That was the feed of the solvent. For the flake, we specify the flakes as we did not simulate the pre-treatment. This part is just after the treatment of the flakes. So we specify 16.6 cubic meters per day of the PET at 25 degrees and one atmosphere. For the water, we started the process without the recycles. So we usually when you have recycles, you start your process with probably a dummy stream on an estimation of how much water will be added to the process. So in this case, we added a ratio of 1:1 in comparison with the GBL of water into the system. So after we have all our feed streams, we go ahead and went through a cooling process, and then the swelling tank, where we choose to use a flash unit operation. In here, the solvent was in contact for the first time with the flakes, and in this specific step, the polymer expands and become like a kind of like a gel, but the polymer is not fully dissolved. So after the swelling tank, we send this mixture to increase pressure and to heating, and then it went to the dissolution tank. We also choose a flash unit operation for the dissolution tank that usually at this stage is carried out with elevated temperature. This temperature was the temperature that we used was 170 degrees Celsius. In this step, the flakes dissolve in the hot solvent and which selectively dissolve the flakes but leaves behind some impurities like fillers or other polymers. So the product from this step went straight to the first filtration for the PET. Oh, sorry. For the first filtration, we use a component separator. In this, the undissolved impurities filter out, and this helps to separate the PET from the contaminants, such as maybe pigments or labels or plastics. We use a component separator so that because in a process simulation software, we cannot actually predict if there is any pigments or labels or any other plastics. So what we did here is just to estimate how much of the probably PET were waste. So we account for the 0.9% of the PET out of the system. Something that I forgot at the beginning of my explanation is that the PET is solid, so we need to specify the component as a solid in the solid components. So in here, we created the PET unifact, and we told CHEMCAD that PET was a solid. So it doesn't get included in the vapor liquid equilibrium calculations. After the filler, it went into cool down, and this is waste. Okay. The product from the filter, which is the solvent and the PET, it goes to the precipitation tank. After the PET dissolved in the hot solvent is a homogeneous solution. So in this stage, it is well mixed. The solution is well mixed with the PET, and it gets in contact with the anti-solvent. The anti-solvent triggers the precipitation in this case. And the anti-solvent, as I said before, is the water that is coming from this recycling right here, and was added at the beginning without the recycle loop. The product for the precipitation tank goes to it's the polymer that is still residual solvent and moisture, which must be removed before the material can be reused in here. So it goes to another filtration. In this case, we use a filter in CHEMCAD, and we specify the geometry of this filter. So we specify the filter area and some of the cake properties and characteristics. Part of the product from the filtration is the GBL water mixture, and the other part is the PET. So let's talk about what happens with the liquid. So what happens in the filtration is a separation of the solid from the liquids, and that precipitated solid goes to drying and cooling, and the liquids goes to a recovery step. So it goes to a distillation column in here, where the solvents are and the anti-solvent are recovered and recycled back to the process. On the PET side, it goes to, as I said, it goes to drying process, where we specify the temperature of the final product, and then goes to cooling until we get the final product in here, which was a clean PET, recycled PET, and we recover 16.4 cubic meters per day of recycled PET without contaminants, and closer to virgin polymer quality. So in this case study, after we did the simulation, we checked the total heating utilities requirement for the whole process, which was approximately 26 gigajoules per hour. We account for various steps involved: cooling, the heating, cooling, the precipitation, and the recovery. So we, in the distillation column, We specify the number of stages, and we specify also what we needed to get from the condenser energy boiler. So CHEMCAD calculated the heat duty and the condenser duty. We use that energy to calculate the total heating requirement for this approach. In the paper, we compare the energy consumption across different method approaches. This one that I'm explaining right now is the anti-solvent, but we also study other approaches such as the evaporation and cooling methods. For more information, please go to the website and look at the whole study. In CHEMCAD, you can also do some simple economic evaluation because CHEMCAD provides preliminary cost estimates for different type of equipment. To take advantage of this feature, in a simulation like this one, you will define, for example, equipment geometry, or it can also be done by, we have some sizing tools that will allow you to generate the necessary geometric data based on your process specifications. And here is the tab for sizing different equipment in CHEMCAD. If you have the geometry, you can go to the equipment cost estimation tab and specify the geometry of your equipment. CHEMCAD then combines this geometry and the mass energy balance calculations and cost indices to estimate a preliminary cost of each unit operation. So in this case, if I check here to run costing report after calculating unit, and I click on OK, I can run my flow sheet, and the calculation converges in less than 1 second. I can go back to my cost estimation tab, and I can see that CHEMCAD can give me some preliminary purchase cost and installation cost. In general, CHEMCAD generates a detailed cost report, which can serve as a strong starting point for a more in-depth economic analysis. You can do this for several unit operations in CHEMCAD that has the tab for cost estimations. Additionally, CHEMCAD can calculate key financial metrics such as return on investment or ROI, profitability, and overall financial performance over the full life of the project. For that, you need to have the cost estimations for your equipment, and here it is the tab that would allow you to create like different cases for to calculate the financial metrics for your process. To wrap up, here are some best practices for modeling plastic resin recycling in CHEMCAD. Begin gathering or estimating necessary data that you need. These often involve reviewing previous research and process-specific studies to try to find some thermophysical properties and behavioral data for the resins. As I mentioned, you can also check some websites for at least for polymers that can give you some data as a starting point. It's essential that you have a clear understanding of your process, identify all of the unit operations, define the functions of each one. In early stages, please keep things simple by selecting the most straightforward unit operations that still meet your modeling objective, helping to avoid any necessary complexity to your simulation. Finally, choose an appropriate thermodynamic model based on the requirements of each step in your process, considering factors like phase behavior and involved in availability of the experimental data. I also mentioned that you can do some cost estimations when you have your simulation already built. And don't forget, if you need any guidance, please reach out to our support team. They are experienced, responsive, ready to help you build accurate and effective process models. For those not familiarized with our software, CHEMCAD is a process simulation software made by ChemStations under the umbrella of DataCore. This tool helps engineers and professionals in different industries to create accurate models of complex or simple processes to improve efficiency and make data-driven decisions. We started more than 30 years ago doing simulation, and we are present in more than 113 different countries. We have distributors around the world, and many universities use ChemCAD to teach process design. What will be the next steps? Please look at the online help material and review case studies and technical papers in our website. At the bottom of this slide, I have again the link of the study that we make based on for the circular economy of PET. You can watch this video and other recorded webinars in our YouTube channel, the ChemStations YouTube channel. If you're not a user, you can request guided demos. If you're a user, you can also request some demonstrations for your team on how to use ChemCAD in different ways. Also, you can request an evaluation if you're not a customer. Thank you for your attention, and I'm open to any questions you have. Noel, can you help me with some of those questions?
Hey, Alejandra. Yeah, we do have a few questions. If you guys can direct your questions into the Q&A chat, I'll try to get to each one of yours, but let me go ahead and read off some of the questions we've already got lined up there. So it says, regarding the flow sheet, do you model an extruder? And if not, do you know how to transform the precipitated PET to PET bales?
We did not model it for this approach. You can perhaps have, to make it simple, in your simulation or in our simulation, we just create the PET flakes. But you can have a different component, like some of the properties will change, but you can create the two components, and depending on the stage that you are in your process, you will have either or. There are some specifications that you need to make in the program. So the program will identify when you have the flakes and when you have the dissolved PET.
And do you model the pre-treatment?
We did not.
You did not. Okay.
No.
Thank you. And so the next question said, regarding the PET component, based on the molecular weight used, it looks like you modeled it based on the monomer unit. Is that right?
Yes. Well, we use the chemical structure to find out and use UNIFAC to try to predict the molecule. So we enter the chemical structure of the monomer. Yes.
And the next question is your model applicable to the recycling of the high density polyethylene?
It might be, yeah. This is, I mean, this is just an example of a simulation that can be done. Depending on the methods that you use for this other polymer, you may use this as the starting point.
And do you have an idea of what green solvents that's recommended for high density polyethylene recycling? Did you learn
No,
about the different? Okay.
I don't have that information, unfortunately. No.
Okay. And then how did you model the phase change from solid to liquid PET during the dissolution?
Yes, there are ways to do that. We decided to go with pretty much the solid and consider that that solid was dissolved. I think I explained a little bit of one of the questions that you made before. There are ways to in CHEMCAD there are ways to specify when you have liquid and when you have solid and when it becomes solid. When you identify the component as a solid, there is an option that will allow you to say, depending on the heat of fusion, when you have the component in liquid state or in solid state. For that, you need to create two components in CHEMCAD. So CHEMCAD knows when the component is in liquid state and when the component is in solid state. There is information about, if you're a current customer, there's information about that in the help system in the program. And if not, make sure that you contact support and they can send you some information about it and guide you on how to do it.
Okay, thank you. And it related to that question, this is the same participant. They're asking, how did you model the impurities, so the non-PET material as part of this process?
Yeah, that will be tricky because when you create your simulation, you need to create those impurities, and I would say that that will not really affect your process when you are simulating it. If you want to see it in your flow sheet, you need to create individual components for that. In a simulator, those type of information, I mean, you can infer how much, an approximation of how much impurities you will get, and then try to maybe use a component separator and separate them. But I will say that they will not be influential in the energy consumption of the process. Sometimes when we think about simulations, we would like to do every single steps that happen in real life. And sometimes you find out that it's not necessary because they are not influential in maybe the goals or the expectations for that you are thinking of getting from the process simulation software.
Okay. And so also related to that, there's a couple people that are interested in how you're able to get, material energy cost and like the dimensions of a filter or like a solid liquid separator. If you're not modeling it specifically, you're just modeling it as a component separator.
So what was the question in that?
So
So
the first part of that is, I mean, this is the same person. They're asking about, modeling phase changes and, the solid liquid separation. So they're also asking, they want to retrieve the material and energy costs of the solid liquid separator. So, if you're uncertain about some of those components, how do you able to extract like information about that separator, or like how do you know the dimensions of a filter to separate solid PET from like the liquid?
well, a lot of um, and I mentioned this at the beginning. A lot of things that you will consider for this type of processes it comes from like different other research that have been made. So you can get some information on what has been used in the past to do this type of recycling and get some estimated geometry and use it in the program. Um, if you use, of course, if you use a component separator, in that case, you will be assuming how much of the impurities you will get out and how much of the actual good PET will be back to the process. Um, I also mentioned that there are some sizing capabilities that you can do in CHEMCAD. So for example, you can do sizing on the distillation column, and you can do some sizing in some vessels, but you won't be able to do sizing on the component separator because it's just a black box that you use to try to compensate of like the impurities that you will get out of the system. As I said, sometimes when we do process simulation, or when you create simulations, you don't have to be that specific on every single step of the way that you have in real life, because sometimes those are like negligible data that won't be into account when you are kind of like calculating energy cost, which is ultimately what you need to know in order to know that your project is feasible or not.
Thanks, Sally. So the next question sounds like it's kind of related to that, but it's at the beginning of the simulation, the PET is defined as a solid. So does this mean that the PET remains as an inert material, or does it solubilize when mixed with solvent at a certain temperature?
No, it's I mean, as I said, you identify it as a solid, but in some occasions it's just dissolved. It's not a solid. You identify it as a solid because the dissolution or the precipitation of the PET will always go as a solid. It will always, most of the time, goes as the bottom product of the tank. So you don't want to have the program to make calculations of your PET for the vapor liquid equilibrium in, in this type of simulations.
Okay, thank you. Okay, someone's asking if it's possible to get access to your simulation example.
Yes, if you are a customer, well, for sure, we can share. I need to double check with the others of with Michigan Technology University. But I think yes, we can share the simulation so you can take a look.
Yeah, you might have to like scrub it of some information or something. But yeah. Okay, so this attendee says that they are PET producers, with plans for 100% recycling PET. So could you provide advice how to model preparation unit? I'm not sure what that was meant by the preparation unit.
Mhm. Yeah, no, I'm not understanding that question.
Yeah, it's marked as anonymous. So to the person asking that question, if you can reach out to support, that would be great because we're not going to be able to contact you. Anyone that we don't get to your questions today, we can contact you following this webinar to have more one-on-one discussion. But if we are logged in as anonymous, we can't really reach you. So please reach out to ChemCAD support folks, and we'll try to answer more a question on one-on-one. So yeah, we're kind of running low on time here. Oh boy, we have quite a few questions um left. So maybe Alejandra, we can reach out to these individuals one-on-one.
Sure.
Yeah.
As
Okay.
long as they have email addresses and some information in there, we will be able to reach out and answer each of the questions.
Okay. All right. Well, I mean, this has been a great engaging discussion. Thank you for your time, Alejandra. Really appreciate that presentation. And thank you to all the people who attended this webinar. You will be getting a recording. You should be getting an email soon with a link to recording of this webinar and a certificate for all those who attended. So be looking out for those emails from us. And again, if you have any further questions or we didn't get to your questions today, please feel free to reach out. If we have your contact information and you asked a question and we weren't able to get to it in the Q&A chat, then we'll be reaching out to you. So I guess we'll go ahead and wrap that up now, though. But again, thank you everyone for
And
this.
thank you very much for being here, and looking forward for your attendance to other future webinars.